Welcome to all in exam days. This is the atomic and molecular physics. We are here for Zeeman, Paschen-Bach, and Stark effect. We start with the Zeeman effect. What actually Zeeman effect is and what it is for. So the splitting, we studied the splitting of spectral lines. That spectral lines are there and there is a splitting is there. We studied all this effect, all these things. Now what happened? The splitting of spectral line is in presence of magnetic field is what we call Zeeman effect. So what is Zeeman effect? It is the splitting of spectral lines. But important thing is, what is the keyword here? The splitting of a spectral line by magnetic field. So this keyword you have to remember, that whenever we talk about the magnetic field and splitting line, it means it is something related with the Zeeman effect. So the keyword is, you have to remember, Zeeman effect. Now it is a confirmation of the spectral quantization. Okay, Zeeman effect is what? It is a confirmation of spectral quantization. When an atom is placed in magnetic field, see what happened. Actually, atom has charges. Nucleus have a proton, electron is revolving around the nucleus. So when atom is placed in magnetic field, its spectral lines further splits. Okay, without magnetic field it splits, that's okay, but when we placed them in magnetic field, then it further splits, and that further splits into the polarized components. Okay, and that split is proportional to the we can say strength of applied field. Okay, so what important thing you must remember then is that splitting, I'm talking about the Zeeman effect. So splitting is into polarized component. Remember this. Okay, polarized component. And next important thing is that we can say splitting. Again, we are talking about the splitting. Splitting is proportional to strength of field, or we can say applied field, better impact, applied field. Okay, so this is what happened in case of splitting in Zeeman effect. Now Zeeman effect is of two kinds. So we just see Zeeman effect is of two kinds. One is normal Zeeman effect and another is anomalous Zeeman effect. Okay, so what normal Zeeman effect? It is observed for the strong magnetic field, and anomalous is for the weak magnetic field. We will also discuss them in detail. For moving to the normal and anomalous Zeeman effect, just understand the magnetic field and magnetic movement relation with this Zeeman effect. So there is the effect of external magnetic field, and under the effect of external magnetic field, the magnetic moment is associated with the total angular momentum. So we can say the total angular momentum is what we can say J. Okay, total angular momentum J, where J is equals to L plus S. This J interacts with external magnetic field that is what we can say B. And due to this, what happened? Due to this, when this interact with the magnetic field, the degeneracy. Now this is the important point to note, that degeneracy in energy due to quantum number J is broken, and as it brokens, the energy level is there, and the energy level corresponding to the particular J, okay, because J has different values, so energy level corresponding to particular J means that special J, or that single value of J, because J has different labels, this energy level, we can say not energy corresponding to, it's actually energy levels corresponding to this split into, now this split into 2J plus 1 labels. How many labels? 2J plus 1 labels. And this labels is what we get the magnitude of splitting. And what is now magnitude of splitting means that the, suppose these two lines have splitting, or better to this one line get further split into the number of lines. Now we need to find the gap between them, and this gap is what we call the magnitude of splitting, and that is given by, so magnitude of splitting, that is given by delta E, and this delta E is what we call negative of mu J dot B. B is what? Magnetic field. So mu J is what? Mu J is the, I told you, this is what we can say magnetic moment corresponding to the total angular momentum G. That's why we denoted that as a mu J. Okay, so this is the basic thing for the Zeeman effect. Now we move to the normal Zeeman effect. So now we first start with the normal Zeeman effect. So I have already told you the basic thing, brief of this is that normal Zeeman effect is what? It is splitting is due to the presence of a strong magnetic field. So normal Zeeman effect is what? Shown by all lines due to the transition between singlet state of an atom, and it can be explained from the classical theory and also from the quantum theory without taking any information related to the electronic spin. Okay, so what happens is the normal Zeeman effect is a single line. So normal Zeeman effect is a single line of wavelength, we can say suppose lambda naught. Okay, in the presence of magnetic field, means what happened, the single line, better not to get confusion, this single line wavelength in presence of magnetic field get split into three components, and these three components, just understand this, we have a single line of wavelength lambda naught. After presence of magnetic field, it is split into three component, that is lambda naught minus delta lambda, another is lambda naught, and third one is lambda naught plus delta lambda. Okay, and this happens, this is the condition when it viewed at right angle. Okay, right angle to magnetic field. okay, right angle to magnetic field, then it is what we can say the splitting is there. When we started with the Zeeman effect, we talk about the polarized components. So can you say um, uh, what is polarized component observed here? So these are the two polarized component we observed. Okay, so we can say, and these are the plane polarized. So we can say the lambda naught plus minus delta lambda are plane polarized. Plane polarized with electric vector. We can say electric vector perpendicular to magnetic field B. Okay, and if we talk about the central one, this lambda naught, what is this now? This central one, that is what we can say lambda naught, is the wavelength of the source, because this single line also has a that wavelength lambda naught. So we can say the central one is wavelength of the soul, and other two are the plane polarized with the electric field vector. Okay, perpendicular to V. And this source means lambda naught, this source is also plane polarized, but one condition is there. This central plane polarized is what you have to remember, that it is um, parallel to magnetic field. Okay, so what difference between these three lines is just like two are perpendicular to magnetic field, and this central one, the original one, the we can say the source produced wavelength is what we can say parallel to the magnetic field B, and this is what we call sometimes normal triplet. Okay, so this is what normal triplet. We just go in the detail of one normal Zeeman effect. For this, we see that the magnetic field is in Z direction. Okay, so magnetic field is in Z direction, and your angular momentum is processing about the magnetic field. Okay, so angular momentum is processing like this, and if it is processing, it is something like this. And what about the mu L? It is opposite to that of the L because of the negative sign we have seen. It is opposite. So this is what we can say. This is your L vector. This is your mu L vector, magnetic moment, and it is also processing about the magnetic field. So it's something like this. Okay, now another thing, both are processing in this way. Okay, this is the resultant. Now according to the quantum mechanics, quantum theory, the polyelectronic atom, polyelectronic means multi-electron, polyelectronic atom possesses an angular momentum, and this angular momentum we can say as L. Okay, and another thing is orbital angular momentum, sorry, orbital magnetic momentum, not angular, orbital magnetic momentum, and that is what we can say, it's a mu L. Okay, that depends upon the angular momentum L. And what is the relation between them is like, we know mu L, okay, magnitude is something equals to E over 2m times L. And if you remove this magnitude sign, these are opposite because of the sign of electron. So we can say the magnetic potential energy of atom is what? Magnetic potential energy of an atom in presence of magnetic field, it is E equals to mu L